All right, this is the third and final hour of Physics 1C for September 8th, and in this last hour, we're going to talk about how you handle problems in which you don't have point charges. So far, we've talked about the electric field of a point charge, and we looked at the electric field of multiple point charges, but the next thing we can talk about are basically like uniform distributions of charges. I don't know a simpler way of putting it than that. So uniform charged objects. Uniformly charged objects. There we go. So this is going to be things like spheres that contain charge, like rods that are charged, sheets that are charged, like real objects, because real objects are not points. A real object would be like a sphere, like a ball of charge, something like that. So we'd like to understand finding the electric field for stuff like that. And in general, what we do for these type of objects is, the first one we're going to do is a rod. So I'll just use the rod as an example. So let's say you have a rod, and let's say that it's all charged up, okay? Something that I'll show you when we do some demos in our first lab. So you've got an electrically charged rod, and let's say that it is positively charged, right? Suppose I then want to come to some position like right here and ask the question, what's the electric field at that location? We can say a few things. First of all, we could say, well, it's a positively charged rod, so probably the electric field points kind of away from it. Most likely the electric field at this location points to the right. It probably doesn't point to the left. But how do you deal with this object that is uniformly charged? The answer is you break it up into a bunch of point charges. You say, well, I can just split this object up into tinier objects. I can find the electric field created by those tinier objects, right? And I can then find the net electric field at this point. So what we do is the slices that we break this up. Let's think about this for a second before I go into the details. I mean, I very much want to get to the problem we're going to do, but might as well think about it for a second. Suppose we just look at this object in the center, and I want to draw a vector at this location for the charge in the middle. So I've taken my rod, I've broken up into tinier pieces, and I take the part that's in the middle here, and I say, what would the direction of the electric field be at this point for that piece? And you all tell me, what direction would it point? I take the piece right in the middle, okay? I come to this point, it's going to go to the right, exactly. I'm going to draw these freehand just because. Okay. It's going to go that way, right? What if I look at the point that's directly above it? So I look at this point right here. What direction is the electric field for that one going to go? The answer is always the same, by the way. Ange has the really good answer. It points away. You can always say away. That's always the answer, because it's a positive charge. If it's positive, it's away. What direction away? Well, it's going to point kind of along a line. So for that one, it's going to point kind of down and to the right. If I go to the next one up above it, it's also going to kind of point like this. If I go to the one at the very top, you get the idea, right? Starting from the bottom, when I come to this one, it's going to kind of point this way. This one's going to kind of point up this way, and you get the idea. For every segment that we break this into, you're going to get an electric field vector. They're all vectors, so obviously we can add them all together, right? And that's all we have to do. It's easier said than done, but that's basically going to be our strategy here. So does that overall strategy make sense before I start showing you the mathematics? Okay. So how do we break these things up? Well, when we break them up, there's really two different ways to do it. But the way we do it in this class, usually, is we take that little piece right there, right, between those 2 points, and we say it carries, let's use the one at the top, actually. We say between this point and this point that there is an amount of charge that we're going to call dq. So a little d and a q, right? Okay, so one segment has charge dq, okay? And then we say that the electric field created at some location, right? So we'll pick one of these. Let's say it's this bottom one right here. We'll call it dE. The electric field, we're going to call dE, and we're going to say it's equal to K times dq over r squared. Now, what do these things mean if you haven't seen this type of notation before? dE is like a differential E, which really just means a tiny piece of electric fields. dq, a tiny piece of charge. To compare this to something that you've probably seen before, suppose that I tell you that this is the origin of a coordinate system, and I draw a line out to this point right here, and I say it has length x, and I want to have a small increment in the size of that. Well, I can say that we can add dx to this, and we can say that the length from here to here is going to be x plus dx. So what does the dx mean? It means a small incremental increase in x, right? It means you're adding like a very, very, very tiny number, okay? If x was like 1,000 meters, you might be adding a millimeter, okay? So that's the dx. This is the dq. So the dq means just a tiny piece that we're cutting out of it, right? And then, if I want to find the total electric field, I'm going to have to add up all the individual electric fields created by all these objects. And the way you're going to do that is you're going to integrate k dq over r squared. And this is going to be what we're doing in these problems now. That's what we're going to be doing. No more r hat, although we can talk about it. But that's going to be the kind of the general strategy that we're going to use to solve these type of problems. Now, one thing you're going to need to know and understand before we even get into this is the concept of charge density, okay? So we're going to talk first about linear charge density, because that's going to be relevant to the first problem that we're going to do. Suppose that I tell you I have a rod, right? And I tell you that this rod's positively charged. And I tell you that the total charge, we'll call it Q total, on my rod right here, let's say is 2 microcoulombs. And I tell you that the length of the rod is, I don't know, let's say 0.25 meters, or about a quarter of a meter. Okay, that's the length of my rod. So I tell you that the length is 0.25 meters. That's an L. Then I can define a quantity called linear charge density, right? I'm going to use the symbol lambda. This is linear charge density. Is going to be equal to the total charge divided by the length. In this case, that would be 2 times 10 to the negative 6 coulombs divided by 0.25 meters. Dividing by a quarter is like multiplying by 4, so this is going to be 8 times 10 to the negative 6 coulombs per meter. That's what lambda is. This would be for a uniformly charged rod. It has 8 times 10 to the negative 6 coulombs per meter. Right? Does that make sense to everybody? The idea of what linear charge density is? Lambda? Lambda, this one? It's like lamb, like the pet, and then or the animal, and then that lambda. Is that what you're talking about? Okay. So that's linear charge density. Now, if I were to ask you, let's see if you all can figure this out. Suppose that I cut the. Ask a couple questions. Suppose I cut the rod in half. Oops. Click on this. Suppose I cut the rod in half. How much charge is there to the left of the cut that I made? How much charge is on the left side over here? If I cut it right in the middle. Take my charged rod, I cut it right in half, and I ask, how much charge is there over here to the left?
One half Q.
Yeah, so 1 microcoulomb, exactly. You divide by 2. Yeah. That's easy, right? Let me ask a more complicated question. Or let's ask another easy question. What if I cut the rod into a quarter, so I cut it again, so that this is 1/4, this is 1/4. How much charge would be here in 1/4 of the rod? Q over 4, right? So that's easy too, right? All right. So let's ask something that's even harder. So the answer is 0.5. Yeah, 0.5 microcoulombs. How much? Oops. How do you calculate that? How much charge is contained in a 1 millimeter slice of the rod? How would you calculate that? So we make a little cut here, and I say that it has, the cut that we make is going to be 1 millimeter. How much charge do we cut out, and how would you figure it out? I'm more interested in seeing an equation. You integrate over the cut. You don't need to integrate. No, it's not quite that hard. Q divided by lambda. Q divided by lambda. Okay. Q divided by lambda is going to give us the length of the rod. How about lambda times the distance? That is the winner. Stefan, you are right. And if someone already said that, I apologize. What if we take lambda? Let's call 1 millimeter. I'm going to give it a special name here. We're going to call it dx. Okay? We're just going to call it dx. Don't worry too much about that. It's a distance. We're calling it dx. It's 1 millimeter. If I take lambda times 1 millimeter, that should be equal to the amount of charge, and guess what? I'm going to call that dq. We're going to say the amount of charge contained inside of the slice is dq. If you take lambda times the distance, so in case, let's do the calculation. 8 times 10 to the negative 6 coulombs per meter, multiplied by dx, which I'm saying is 1 millimeter, so that's 0.001 meters. I'm going to get an answer that I'm going to call dq, and my answer is going to be, it looks like 8 times 10 to the negative 3 coulombs, right? Now, 8 times 10 to the negative 9 coulombs, or 8 nanocoulombs. Right? 8 nanocoulombs. And it's not important what the answer is. What is important is that you understand the equation and how to use it, because it's going to be essential to solving these type of problems. Lambda times the distance. And if you think about it, that's what you were technically doing in the previous parts, whether you knew it or not. When I asked how much was in half the rod, well, you just said it's half, but really what you should have done, if you thought about it, was take the length of the rod and multiply by lambda. Take the length of the cut and multiply by lambda, and that's going to give you, it's going to make it work. So you take density times distance, you get the charge. This is an incredibly important equation that you're going to need to use in these type of problems to be able to do the integral. Does anyone have any questions before we start? It's exactly like linear mass density. You're 100% right, Patrick. Does anyone have any questions? You feel like you understand what charge density is? It's just the charge per unit length. That's all it means. That's all it is. Lambda is the charge per unit length. And we're going to use it like this because, look, there's a dq right here and there's a dq here, and that's how it's going to be used. So, now we are going to solve this problem. So we're now going to be looking at charged lines, charged rings, charged disks, and yeah, that's it. And I thought we would get through at least 2 of them today, but I'm not surprised we only get through 1. That's not a problem. We'll catch up later. So what we're going to do is we're going to find the field of a large charged line segment. So it says a positive charge Q is distributed uniformly along the y-axis between negative A and positive A. Find the electric field at a point P on the x-axis at a distance away from the origin. So we're going to start off with a rod. That's our rod. We'll make it red. We'll make it this color is fine. So there's our rod, and we'll make it a little bit skinnier if I can. This rod carries positive charges. It is along the y-axis between negative A and positive A, so I'm going to draw another line in here to represent the x-axis. So we'll draw a line right through the middle. It's pretty much through the middle. That's going to represent our positive x-axis. The y-axis is going to go up and down. It says it's distributed from y equal to negative A to positive A, so we're going to say that... this thing's set up right. We're going to say that positive y goes in this direction. We're going to say positive x goes off in this direction here. And we're going to say this is A. We'll do it like this. This is y equal to A. This is y equal to negative A. This is the origin. Right here is the origin. That's what we need. I will also say this distance is A and this distance is A. And those are A's, whether they look like A's or 9's. Those are both A's. Okay, so we have a positive charge distributed throughout this, right? So let's go ahead and throw some positive charges in here. I was going to try to make it red, but the pointer decided it didn't want to accept my input. Positive charges distributed throughout this, and we need to find Positive charge, capital Q, so Q is equal to the total charge. How long is the rod, by the way? It's 2A, right? Distributed uniformly, that's important, along the y-axis between y equal to negative a and positive a. Find the electric field at point P, at a point P on the x-axis, a distance x from the origin. So we're just going to pick a random point right here. We're going to call that P. We're going to say it has a distance x from the origin. We want to find what is the electric field at that location. That's our goal. So let's figure out some things that are going to be relevant for us before we start doing the calculation. What is lambda? What is the linear charge density going to be? I will scroll back up a little bit so you can see the definition. What is lambda going to be in this case?
Q over 2A.
That's exactly right. You take Q, you divide by the length, that's Q, divided by 2A. Perfect. Okay, scrolling back down again. Now what we have to do, and this is the part that's kind of tricky, and you're going to have to do this on your homework a couple different times. Can I please just get this thing to work? So, please pay attention. You're expected to do all the steps that I'm about to do. Most people skip out on a bunch of them and they miss all kinds of points they shouldn't miss. First step for doing problems like this is we are going to take our object and we are going to cut it up into tiny pieces. In particular, I'm just going to cut one piece off right here. Right? That's one small segment of it that we're taking here. Let's shade it in and say that that is going to be a charge. It's a piece of the line segment that we call dq. It really just means a tiny piece of the line segment. And the piece that we choose, we're going to say it has a y coordinate that we're going to call y. So y is going to go from here, obviously, down to there. That's y. In fact, I probably don't need to put the lines on there. I think you probably understand that y is the length of this side. Get rid of this in case it's confusing. Next thing that we're going to need to do is we are going to need to figure out the electric field due to this one charge. Okay? That is our goal. We're going to find the electric field due to this one little charge right here, and then we're going to integrate over the entire rod. We're going to add up all the little electric fields. So the first thing you do after drawing the piece of charge, the next thing you're going to do is you're going to draw a vector to represent the electric fields. Now, in order to do that, I'm going to need a couple lines on here. So the first line I'm going to draw from here to here. And I'm going to label that to be r, because we're trying to find the electric field at point P, and you always need to know the distance r away. So we'll go ahead and call that one r. Now, I need to draw the electric field at point P. What direction am I going to draw it? Well, the rod is positively charged, so you all tell me, what's the electric field at point P? What direction does it go? Do I make it point off this way, this way, this way, away towards, what's the answer? Northeast, southeast. And even though this problem is a little bit different, we're just looking at this one positive charge. Imagine if it was a point. Imagine this is a positive point charge, and I want to figure out the direction of the electric field at point P. What direction is it going to go? Down to the right? Only one answer. Give other people some time. Down and to the right? Yeah, it always goes away, right? It always points away. So, definitely down and to the right. Someone's mic is making noise. I'll figure out who that is. Wait, I don't see anybody's name lighting up. Is that just on my side? Do you all hear the static? Let me unplug and replug in my headphone. Where's that coming from? I'm gonna stop the stream. What on earth is creating that noise? Yeah, I'll leave it and join. Oh, is it gone now? Or the person left, maybe? You're still hearing it? I don't see dong. It went away when I left and came back, though. Oh, the joys. The joys of teaching on the internet. It's just the best. This is what I wanted to do when I went to college. I was like, I hope someday I can just teach on the internet. Okay, but I don't. I'm joking, of course. I don't hear anything at all. I rejoined, so I would suggest leave the channel and come back. I'll give you all a moment to do it. Yeah, I don't hear the static anymore either, so. Alright, let's continue going. The recording never stopped, so I guess that's that going for us. Okay, to get back to what we were doing. So, we have this line segment, it has charges on it, right? And we've broken it up by taking a little line segment right here and just saying, like, we're going to cut a little piece out. We're going to call it DQ. We're going to treat DQ as a point charge. It's positive. So we drew a line from there to the point P and labeled that as R because we're trying to find the electric field at this location. And now we asked, what's the direction of that electric field? And I said it's going to point this way. And then I said, we're going to call it DE. All right. And there's going to be an angle. We'll call it theta here and here. All right. So we know from what I just wrote down a second ago that the size of this electric field, DE, is equal to K multiplied by the charge, which is DQ, divided by the distance between them squared. Now, this equation isn't very useful to us because, for example, if I want to try to integrate both sides of this, you can't immediately do the integral. Why not? Why can't I immediately do this integral right here? K is a constant, so you don't need to worry about that one, but... Set up DQ. Yeah, that's what we're going to have to do, Daniel, but my question is, why can't I just do the integral? Why do we have to mess with all this geometry stuff? Why can't we just get down to business and do the integral? Why am I wasting my time? Wasting your time. R and Q. Right, so this tells us, when you have an integral, you have a variable of integration, which in this case is Q, and you have something else that's a variable, which is R. R and Q do not share the same variable. So if it was dr over r squared, then we could do it, but Q and R are different. So that means that we need to get dq somehow into some form that looks like r or something like that. Okay? All right. Now, there's something else going on here that's important to understand. So dE is actually a vector, right? But I didn't write it as a vector. Now, when I think about that dE, I notice that it can be broken up into components. I can break D up into components that point like this, a y component, and like this, an x component. We'll call this one DEX. We'll call this one DEY. And I'll just say that if we call DE the hypotenuse, then DEX would have to be DE cos theta. And DEY would have to be DE sine theta. But because the DE sine theta points down, right? Suppose that I had chosen a piece down here for my DQ. I drew my line. I drew my DE vector. The DE vector would point something like this, right? And then it would have an upward component. I'm going to erase all this stuff. It would have an upward component DEY that would go this way, right? But if I make sure that the distances down here is negative y and y, then what can I say about the DEY here and the DEY here? If I choose it, they can cancel exactly. So what that means is, and now again I'm gonna erase all the stuff that I just wrote because I don't want to make things too complicated. But DEYs will cancel because of the symmetry of the problem, because we chose a point that's right in the middle. Now that might not always happen. You all will have a problem with this doesn't happen. But what we can say is that the DEYs will cancel. And I'm just going to say due to symmetry. So that means that we only have to find DEX. Well, DEX should be equal to, I'll add one more step in here, as we said right there, DEX is DE cos theta, so we need to put that in here as well. So that's going to be DE times cos theta, which is going to be KDQ over r squared times cos theta. Okay, this is the part where things get, I I hope up till now this all seems like we're not really doing anything super new, but the next few steps will be very different from what we've seen so far. So now we have to think about what's going on in the problem. We have this dq right here, right? And what we would like to do is we'd like to rewrite it in terms of some other variable. So what we're going to do is we're going to say that the thickness of the piece that we cut here is going to have a thickness dy, or a length dy. And then we'll use the equation that we had from above, which was that dq was equal to the charge density lambda multiplied by dy. Okay? You take the charge density, you multiply by the thickness of the thing you're cutting out, that gives you the amount of charge you have. So let's put that into our equation. But even before we do that, now let's go ahead and do it, because we'll go step by step. So we have now dex equal to k. We're going to replace dq with lambda dy. I'm going to tell you all right now, I'm going to go 10 minutes over because we not only got started late, we had a lot of interruptions during the class. If you need to leave at 4:20, which is going to be in about 4 minutes here, feel free. I'm going to have this recorded. It'll be up on YouTube. You can watch it later if you want to, but we need to finish this so that you can be prepared to do your homework. So I'm just going to go 10 minutes over. I'm stopping at 4:30. I'm not going to tell you when time's up. You can leave if you want to leave. Again, it's all on YouTube. Okay, so dex, we replace this dq with lambda dy, right? And now we ask, can we do the integral? Almost. I left something out. There's a cosine theta here. We can almost do it if only we could write r in terms of y. Maybe we could do that. Let's look at the picture. We've got a right triangle right here. It has x as one of its legs, y as the other leg, and then r as its hypotenuse. X is a constant. X is a number that we're just going to pick. This is a constant. So we can write r in terms of y and x, right? How could we do that?
Square root of x squared plus y squared.
Exactly. Where can I write that? I'll just write this right here. We know that r squared is equal to x squared plus y squared. That's great. Let's plug this into our equation. We're getting closer to being able to actually do the integral. So we do k. We know what lambda is, but it's a constant, so I'm going to leave it as lambda. Obviously, dy doesn't change. We're now replacing r squared with x squared. I remind you, x is a constant. It's the distance from the axis. We're holding this value constant. Plus y squared. That's the value of r squared, and this is multiplied by cosine of theta. Now we're really close, because now it looks like we could do an integral, right? K and lambda are constant. We don't have to worry about those. We can pull those out. We have an integral of dy over x squared plus y squared. We should be able to do that integral, because x squared is just like a number, right? It could be 9 squared or something like that. But the cosine theta is sticking around here, and so what we have to ask ourselves is cosine theta going to be a constant? Now, looking ahead, what we're doing is we're doing an integral. And when we do an integral, what we're going to be doing is we're going to be looking at different cuts dq, meaning that we're going to go through this rod, we're going to take cuts all along here, we're cutting it all up into pieces, right? So we've got like a cut right here, we got like a cut right here, we got a cut right here. And what you have to think about yourselves as you're doing this is, suppose that I were to draw r's for each one of these here, right? I ask the question, is the value of r changing for each one of these pieces? And I hope for you, if you're following along, if you're keeping up with this, I hope you all would agree that the value of r is going to be different depending on each one of these, right? In fact, it's going to get smaller and smaller and smaller to get to the middle. It'll start getting bigger and bigger and bigger again. Okay. What else is going to change? What about the angle theta? Suppose that I picked a point up here. Would the angle theta be different if I picked a dq up there? It would, right? Okay. So now we have an idea of exactly what's changing in our problem, and that's the key. You need to know the things that are varying. So the things that are varying in this problem are the value of r and the value of theta. They're changing, right? That means we need to do something to get rid of cosine theta here. Now you have two options. You can either take your entire thing here and put it into variables that only involve y, or you can take all of this and put it into theta. Those are your two options, right? You either put everything into you put everything into y's or thetas, or actually you could put everything into r's if you want to as well. We're going to do it two ways. I think we have time to do it both ways. The first thing we'll do is we'll say, what is cosine theta equal to? If I look into this triangle right here, I would argue that cosine theta, maybe you can type the answer before I write it, or you can think it at least, is equal to x over r. Would you all agree? And that means that cosine theta is also equal to x divided by the square root of x squared plus y squared. right? So we plug that in here, and so now we're going to get dEx is equal to k lambda dy over x squared plus y squared times cosine theta is x divided by the square root of x squared plus y squared. And now we're in business, because now there is only one variable now, right? Only one variable remains, and it's y. I know x looks like a variable, but trust me, it's a constant in this problem. Only one variable remains, and it's y. And that's perfect, because now we know we can do this integral. So now it says that dEx is equal to k lambda x times dy divided by x squared plus y squared to the 3/2 power. There we go. There we go. And that's an integral we can do, right? Now we can integrate both sides. I knew that wasn't going to work. Now we can integrate both sides and solve the problem. So let's see what we end up getting. When I sum up, remember this integral now that you're doing, you're really summing up individual values of dEx. You're taking the value of dEx for this angle, for another angle, for another angle, for another angle, every single piece of it, and you're accumulating them all up together. You're summing them all together, almost like a Riemann sum, but you turn it into an integral where you make the size of the cut super small. And we're going to get k lambda x integral. I'll let you all tell me. Tell me in the chat, what are the limits on my integral going to be? What are the limits on my integral going to be? Negative a to a. Yep. Negative a up to a. In fact, if we want to, we could probably do double the integral and only go from 0 to a if we want to. All right, we got to do this integral now. How do you do that integral? We almost finished in time. Technically, we did, because the rest of this part's math. We got to an answer, so we pretty much finished in time. How do you do this integral? Well, I think you want to do... I guess I'll give you some options. Should we do a u sub?
U sub?
Let's do we do a u sub? Do we do a trig sub? Which is basically the same thing, but using trig. Do we do integration by parts? What do you all think? I see a lot of trig subs. What do you think? What do you use for the trig sub? You remember that part? What is the trig sub you use for these kind of things? Yeah, Tom Bui's right. Here's what we're going to do. We're actually going to go back and redo it in terms of theta. Pretty much. That's pretty much the right answer. So I'll just tell you that even if there wasn't a picture right here, what you can do is you can use I think it's y equals x tan theta. And lo and behold, if you look at our picture, that is what y is equal to, right? Y is actually equal to, see, tan theta is y over x. Anyway. And then what would dy be? Dy would be secant squared. And then we plug everything in together. So we're going to get E equals k lambda x integral. Dy is going to become x secant squared theta. We're dividing that by x squared plus x. We plug in for y squared, x squared tan squared theta. Whoops, there's a d theta on here. My bad. D theta. And then we'll deal with the limits here in a second. I'll put the limits on at the end. So it's going to be k lambda x integral. And now this whole thing, and then I'm being super sloppy because we're running out of time. I really shouldn't be. So sorry. This to the 3/2 power. So all I've done here is for x squared, I wrote that back down there. Y squared became x squared tan squared theta. Keep the 3/2 power. The numerator, there's still a d theta right here. And then what we do is we use the relationship. I'm just going to go ahead and assume it's probably the case that 1 plus tan squared theta is equal to secant squared theta. Is that right? Or is it? Let's see. Sine squared theta plus... Is that the correct one? In case you don't know, this is how I always do it. I'm like, how do you get the answer? How do you get the top one? Well, you just divide by cos squared. And this will turn into this. It looks like it's right, because you're going to get tan squared plus 1 is equal to secant squared. So that means that we basically have x secant squared theta d theta in the numerator, but the bottom is actually x squared times times secant squared theta, and then all of that is raised to the 3/2 power, basically replacing x squared plus x squared tan theta with x squared times secant squared theta. It's all raised to the 3/2 power, which means now what we get is k lambda x integral x sec squared theta d theta divide by, so it's x squared to the 3/2, which is x cubed. Checking the chat to make sure I didn't make a mistake. Secant squared theta, so this is secant cubed theta. Feel like we haven't made any mistakes yet, but I easily could have. So what's left over? Well, you have an x times an x divided by x cubed. That's going to be k lambda over x. And then what's left in the integral, I believe, is just secant theta. In the numerator, no, it's cosine theta, right? Because it's secant squared divided by secant cubed, which means you're going to get 1 over secant theta. And so you get this really nice, simple cos theta d theta, easy as pie to integrate. And now we do need to put the limits back in. So before our limits were negative a equals x tan theta. So I find that this is actually the part where it might be better to, I don't know. But so that means negative a equal to x tan theta, which means that theta is equal to the arctan of negative a over x. And that's what the lower limit's going to be. I hate writing that in here, but I'm going to have to. Tan negative 1 of a over x is the lower limit. The upper limit is going to be the arctan of a over x. Sorry, this was the negative one. Oh, this is getting so sloppy. Equals, we can write this very large so it becomes obvious what I've just done. So k lambda over x multiplied by, the integral of cosine theta is sine theta, right? So we have sine theta, and we need to evaluate it between the limits of the arctan of a over x and the arctan, this is the negative one, and this is the positive one. When we plug these things into here, we're going to get k lambda over x. Now, the sine of the arctan of a over x, what is that? So if this is a, and this is x, then this is going to be the arctan of a over x. And the sine of that angle will be a divided by this side, which is going to be a squared plus x squared square root. So that means that the sine of the arctan of a over x is the same thing as the ratio a over square root a squared plus x squared. And then if it's a negative sign, that's going to be like a triangle down here, where now you're going to have the tan negative 1 of negative a over x, where this is negative a, and now the sign is going to be minus negative a over square root a squared plus x squared. So the minus sign right here is from the negative a. The minus sign right here is just from the way you do integrals. So finally what we get is that we get 2k lambda a divided by x times the square root of a squared plus x squared. The calculus alone takes quite a bit of time on this problem, and I went through it way faster than I normally would. Normally what I would do is just have you as students do that yourselves. But I think that's the right answer. You can check in the book. We can also check to make sure it has the right units. That's the easiest thing to do. Oh, there's another form of this because lambda was q over 2a. So if we plug that in here, you're going to get kq over a, which will cancel out that a actually. So kq over x times 1 over the square root of a squared plus x squared. Can I pull it up? What, the book? Is that what you mean? Sure. Is that what you mean? I don't know if that's what you mean. But I'm virtually certain that's the right answer. It has the right units, and it reduces down to what I would expect it to reduce down to. Oh, roll it up. You want me to just scroll up, basically. You know what I'll do? We'll just do this. Just go out a little bit here. Does that help? But this is the answer. This is the electric field of a charged line segment at the midpoint right there. And I know that's very, very complicated, but you can always pause, rewind, watch it again on YouTube. I would highly recommend that when you're doing the first homework problem from the lab manual, that you keep in mind how I did this, because it'll definitely help. Yep, I have to stop. It's 4:30. I'll stick around, but I'll be happy to answer questions as well. Okay, so I'm going to stop the recording now. Our next class is Monday, and I will see you on Discord on Monday. When this will be uploaded to YouTube, I usually do all my uploads at the end of the night. So I have another class, so it'll be up there at the end of the night, if that's okay. All right, stopping the